Thank you, Lucas. Thank you. Let's do this. So, hello everyone. My name is Yannick Héneault. I'm a French-speaking Commodore 64 enthusiast. So I will try to do my best with English. Sorry if it's not perfect. So, a little bit about myself. I'm a computer engineer with some expertise in embedded electronic. I've repaired a couple of Commodore computer in the past. I also designed some piece of hardware like this Christmas cartridges. Some people has Pi 51, also that design TapeMate64, Wi-Fi modem. So I'm a little bit in that area in terms of retro computing. But today what I will present it is this new little device that I call TapeMate64. Sorry for the people in the back, come after to see it. So I have a lot of material, so please keep question for at the end. There will be a period of question. So what is TapeMate64? So basically, it's a solution to digitize Commodore 64 tape or VIC-20 or PET tape. So, sorry, it can also write a real tape image from your PC back to a real tape to use it in a real computer, but it's mostly for the nostalgia effect. The main idea was for archive or preservation of tape. So with the solution, it's only the device and the dataset. You don't need the real Commodore 64 unless you write a tape and you want to run it. Otherwise, it's just the device and the dataset. So just before giving too much details about TapeMate, I will just do a quick recap about how data tape work in a brief tour of the existing solution to convert tape. It's already existing since a long time ago, so I will just present them. So here we have an image of a signal of the waveform that you could find on the data tape. So from the graphic, we see that we have this middle zone here, and the dataset itself is doing a conversion from analog to digital when the signal crosses the middle zone. So it's based on the rising edge or the falling edge. So every time depending on the direction, the dataset connector, so at the output here, there is a TTL pulse that we call that change the orientation, based if it's rising or falling. Sorry. Somebody could think that, hey, this is the binary signal and it's the one and the zero. This is not. It's just a TTL level. There is to interpret the binary code, the key is the falling edge. That is important. The time between two falling edge is computed by the computer, and this is what tells it if it's a 0, a 1, or some synchronization markers. So how the Commodore 64 can do this? For this, it used the CIA. It's not the American agency, but the CIA chip from the computer itself. So this is a snippet from the schematic of the Commodore 64. So the CIA has an internal timer that is clocked by the P2. It's the system clock, sorry. So it's triggered at 1 megahertz, more or less, depending if you're using an NTSC or PAL system. Sorry, it's around that. So the timer is counting from 0 to 65,000 approximately, and then go back to 0 and turns on. Sorry, I'll just take a bit of water. So when there is a falling edge that is coming from the dataset, it triggers an interrupt inside the CIA, and this is sent to the CPU. And the first thing that the CPU is doing in this interrupt handler is reading the value of the timer, and by comparing with the previous value, can determine the number of pulse, sorry, and check if it's a 0 or 1 or some kind of synchronization. So about the pulse themselves, we can split them in two categories. There is the standard Commodore loader, which is very slow. Most people already experimented that in the past. So it's around 50 bytes per second that you get, but it was designed for reliability and not for speed. So you have the different pulse here for the 0 and the 1. It's very large. This is to accommodate the fact that not all the data sets are running at the same speed, tape material, elasticity of tape. So just to be safe, they use that. And even more, they duplicate the data twice on the tape. So that's why, sorry, that's why it's taking so much time, because if there is an error in the first version, the Commodore used the second version. Uh, that's why company decide to use a turbo loader to load their tape a little bit faster. So what they do is that they have a special program at the beginning of the tape that gets loaded by the Commodore, and then switch the, the way the signal are handled by the Commodore to use much more smaller pulse. So the trade-off is that it's very time insensitive and it requires precise recording and playback. But you get more speed. You can get 10 to 20 more faster time to load than the regular Commodore. So a tour of the current solution that exists. There is probably many more than these one. Probably the other one fall in one of these categories. So let's start with the first one, the direct audio capture. Some people get luck with that. So you just need a good tape deck, a good tape player that you connect to your PC, and you record the signal. But as I was mentioning, the signal on the tape is a square pulse, it's not audio. So when tape deck are designed for music, they have all kind of filtering, they have equalizer, Dolby, EGC, all that stuff that can alter the timing, the waveform a little bit. So it depends on your millage, it can work or not. It requires also some tuning for the volume at the output and the input to make sure the signal is good. And even if you get lucky enough, you have to use, it's a two-step workflow. You have to use first a software to do the capture, so to get a waveform, something like Audacity, let's say. And after that, you have to use another program to convert the wave file to a TAP file image. I will present a little bit after what is a TAP file, but it's the image of the tape for an emulator. This is what we want to create. So another solution is called MTAP or PTAP. These tools are command line, are very old. They are more than 20 years old. At the beginning of tape dumping, we could say, they were designed for real parallel port. So it's very rare on modern PC. It requires a real PC parallel port. It doesn't work with the virtual one. So you need that kind of adapter here. You need a power supply also, because the parallel port is not able to drive the end of current for the dataset. Since it's relatively old, it's mostly MS-DOS based, so limited support for, let's say, a Mac. Many of the original download link also are dead. While I was searching for this, you can still find information, but it's old. But some people are still using it. If you have the proper hardware, it's working correctly. So another one, this device, the 1530 USB, I didn't have it myself. It seems to have some popularity on the community. This one is interesting. You connect your dataset to it, and there is a USB port. So I thought at first it was similar to this one, but the USB output is, from the perspective of the PC, a sound card. So basically, the dataset is performing the analog to digital. This device is doing the opposite, from digital to analog, sending back to your PC, where you still have to run Audacity to capture the wave and then do the processing. And it's a proprietary device. It's made by a single developer, closed source software, no schematic, no hardware documentation. I was not able to see what's inside. And it's a Windows-only application, according to the seller. Then there is TPUG. There is many versions of TPUG. This is one that I have built. So TPUG is primarily tape emulation. tape emulator for the dataset. So you can connect this one directly to a Commodore 64. There is an SD card where you can put your tap image and you can load and save from them. Yeah, it has screen button for the tape selection, so it's a bit more complex for some people to assemble. It increased the cost a little bit, and it's a tape emulator. But I've mentioned here it in the presentation because, like this one, some Tapino has a connector to connect a dataset in the back. So you can create a daisy chain with a Commodore. So you can connect this one on the real Commodore and then connect the dataset there. So the Commodore will provide the power for the two devices, and the Tapino can feed or the signal or get the signal from the dataset. So it's a possibility to do the conversion, but still a bit annoying because you have to remove after that the SD card, move it back to the PC and so on. But it works. And finally, so the one that I start this project with is called TapeMate64. So it uses a small Attini CPU to measure the pulse duration. So you connect your dataset here, and on the USB side, it sends the pulse information, the pulse timing, back to the PC. So this project itself was derived from the True Tape64, which I think was started during the COVID time. This little board has around a little bit more than 25 components. Its PCB is open source, but it's all surface mount. So it's not very beginner friendly to solder. You need a Twizzle and probably a microscope to assemble this by hand. And Attini microcontroller are a little bit less common than Atmega on the market, but still. But it was a very good project. So I decided to start with that. There was some issue with software also, but it was open source. So I start with that and fork it to create TapeMate64. So you probably now have an idea why I decided to build this little device. So it's using a USB-C connection, so it's not depending on old or obsolete hardware. It's fully open source, so I'm the originator, let's say, but I'm not the single seller. Anybody can contribute. It's pure digital timing pad, a little bit like the CIA I was showing at the beginning. So no conversion from analog and digital. It doesn't require post-processing with Audacity. The old software with TapeMate generate the tape image files directly ready to use. I'll show that in the demo. The PCB, this one that I've designed, it's using TrueHole technology. So you just have to put your component with a regular soldering iron. You can assemble this. It's relatively easy. And you don't need a C64 for the power. There is no SD card, so no SD card swapping. So a standalone device. And on the market, there's still a lot of dataset available that are cheap at good price, so it's easy to find one. So a little bit in terms of hardware, I've decided to design the PCB with module in mind. So the first one on the left is called an Arduino Nano Super Mini. It's available on AliExpress, DGK, most distributor. So at its core, we have an Atmega chip. So it's the brain of the system. It handles the pulse timing, motor control, USB communication. The second one, second module is the MT3608, which is a boost converter. So it takes the 5 volt from the PC and pump up to 6 volt to be able to operate the dataset. All the other components are regular components, one transistor, one optocoupler, 2 resistor, and 1 capacitor, and that's it. And with all that, we are able to drive the same signal as the Commodore is driving on this edge connector. So from the perspective of the dataset, it's a real Commodore that is connected. So here we have the schematic. I will not go into the details, but even for people that don't know electronics, is not too complicated, I think. Relatively few components. So the firmware that run on the Arduino made it as a turnkey solution. So it's easy to flash. From the host application, you just have to click a button and flash the Arduino directly. So no need to install Arduino IDE or Visual Studio Code. Everything is one button. I will show it in the demo after. But the firmware itself is open source. It's based on the Platform.io project. So for people that doesn't know about it, it's a kind of kit for the IDE that control your dev environment. So it downloads for you the toolchain, the compilers, the library, everything. So all the files are already provided for the configuration. So in the README, I provide the instruction to install Visual Studio Code, Platform.io, and it takes care of everything. You just have to click build and upload if you want. So it allows you to easily modify the firmware if you want to try some things. Fix bug, that's a possibility. I try to do my best for testing, but it's a possibility. It's open source. So that's for the firmware. Now on the PC, the whole software that is running, there is two flavors. There is command line tools and an optional GUI. So here I have a screenshot from the GUI. Both versions support reading tab file, writing tab file, flashing the firmware. And if you use the GUI, you have this little window here that can help to verify the calibration of your dataset. And the host application are code in Python, but I provide them on GitHub as precompiled. So it's a zip file, you download it. And for Windows, it's already an exe file. So you don't have to install Python and all the dependency. But it's open source, so you can if you want to modify it. So a little bit more about the calibration window. So on the dataset, on top of it, there is a little hole with a screw for the head adjustment. So if you have something, if you try to digitize a tape and you have something like the window on the left, that's not good. You want something like this. So this is the idea is that on the y-axis, you have the pulse timing from 0 to 2000 microseconds, I think. So if you have something like this, you have pulse duration that are everywhere, so that will probably not work. So here we see that we have distinctly two type of pulse duration. So this is what you want. To do this, you need to be sure that you have a good tape between your hands first. Then you can perform the adjustment. So a little bit about how things work inside the Arduino when you are reading a tape. So first, on the top left, we have the timer inside the Arduino that is running at 2 megahertz, always counting, and everything is interrupt based. So when there is the falling edge from the dataset, the interrupt handler first get the value from the timer, compute the pulse duration from it, and send it to a queue. And that's it, only that. What can happen, especially with turbo loaders, that you can have long pulse. So in that case, the timer will reach its limit of, because we're running at 2 megahertz, it's a 16-bit timer, the limit will be hit at 32,000 microseconds. In that case, there is a second interrupt handler that is triggered, and I call it the overflow counter. So that means that the falling edge didn't come, but timer reaches limit, so it just counts the overflow. And when the real falling edge will come, the interrupt handler will take the value from the timer and take the value from the overflow counter, combine them to compute the real pulse duration, send it to the queue. And in parallel, we have our main application that just read value from the queue, and send that via USB up to the PC to create a tab file. Some special things to notice. Teeny pulse less than 8 microseconds are filtered. You cannot express them in the tab file anyway, and the Commodore 64 is not enough to detect that type of pulse. There is a CRC that is computed by the host, by the device. There is a comparison at the end, so to make sure that you didn't lose any value during the USB communication. And the main application also is handling all the possible stop conditions. So if there is no more pulse for a certain amount of time, if you press stop on the data set, things like this, so it will stop and close the tab file. So when you try to write a tape, it's a little bit similar, but it's the opposite way. So the PC host application is streaming the pulse duration to the device. So at the beginning, it tries to completely fill up the queue, and then it starts the timer, still running at 2 megahertz. And after that, it's the handler and the timer that works together. To the handler take the first pulse, configure the timer. So I don't know if 300 microsecond configures the timer. When the timer reaches this count, there is the interrupt handler. The interrupt toggles the right signal for the data set, pick up the next value from the queue, program the timer, wait, and so on. We still have support for the overflow also, if we need to write a long pulse on the tape. So it's the same logic as before. It's a special case. And in parallel, we have our main program that is monitoring the size of the queue and asking the host application to get more value. So there is a threshold in the queue and it's getting too low. It's asking the PC, give me more value, give me more value, until we reach the end of the tab file. And after that, you get your whole program on tape. So I've mentioned a little bit tab file a couple of times. So it's very easy to understand if we look at one. So first, not very important for the presentation, but there is an header that describes the machine, the version, the video clock speed. But what is interesting, all the data is the number of clock cycle as captured. So you probably see a bunch of 30 there. So if we convert 30, it's an hexadecimal. In decimal, it's 48. And in tab file, they use a factor of 8. So we multiply by 8. We adjust with the system clock. For this example, it's a PAL system clock. So this gives us, if we do the math, around 390 microseconds. So that means that all these 30 in the tab file were generated from a cassette that was doing a train of 390 microsecond pulse. It's simple like this. And when they designed this format, they realized after, oh, we cannot express long pulse because it doesn't fit of the single byte. So they put an extension. So if you have a pulse of 0, it doesn't make sense. So 0 is used as a marker. And in that case, it's the 3 next byte that are used. In that case, in the Little Endian format, there is no the 8 factor, but you still need to adjust with the clock. So if for this sequence, it's around 2,800 microseconds. So, and that's it. You know everything about the tab format. Demo time. Good. So in 3 steps, I will first flash the device. We'll suppose it's an update or if it's a brand new device that needs to be flashed. Then I will read a very small program on this tape to generate a tab file and run an emulator after that to make sure it runs and like the original program. So it's a full end-to-end preservation workflow, in 1 or 2 minutes. So I will connect this. You never know what can happen with demo, but so I'm using Linux, but it's working in Windows also. So I will start the GUI. So we have, I have some light reflection. Sorry. Okay. So first, let's say I want to flash the firmware. So I already connect the device, and boom, it's done. So it's very small firmware. And in the application, like I said, everything is done to flash the Arduino. So no need to connect to install anything new. And then I will capture the tape. So Let's make an original name. Demo tape. Ask me to press play. So we should see the signal. So first it's the pulse synchronization that are coming. And then we will see the 3 type of pulse that Commodore is using. At some point it will freeze because the program is using a turbo loader. So there, now it's freezing. And now we see that the pulse is coming at a higher rate. So everything is transmitted right now to my laptop. And that's it. I can press stop, or after 15 seconds without pulse, it should stop by itself and we'll close the tab file. So let's wait a little bit, take some water. Great. So now I have my tab file. So I can run Vice with and so we found the program C64 matrix. Sorry for the flashing effect, but it's the turbo mode. Yeah. And we have it. So if I run, I did the conversion. So so we go back to the presentation. So we were there. So one extra tool that is not part of this project, but it's an open source from that you can find on SourceForge. It's called TapClean. It's very useful because it can validate a tab file. So if you get one from the internet or the one that you can that you generate yourself, it will check the pulse structure, the block layout, and everything to make sure your tab file is correct. And it can also identify the loader by examining the type of pulse. So if it's a Commodore regular loader or some kind of turbo, like turbo tape, Nova load, and so on. And with that piece of information, what this program can do is a normalization of the pulse. So it can smooth the pulse sequence. So by that, what I mean is, if I go back to the tape format here, this is theoretical. So because in the real life, you will not get this. You will get 30, 30, 31, 2F, 32, 31. There's always variation because of tape, motor speed, and so on. So TapClean is able to identify this and fix the pulse. It should not affect the image by itself, so you can still load it. But what it provides you is you will, if you want to compress your image or zip it, you will have a much more better ratio because of all the redundancy in your data. But still, it's optional. Like you just saw, the tab file by itself is working. But if you want to share it or compress it, that's a nice tool. And so, like I said, my first batch of kit was sold yesterday. I will put a link in the GitHub to get more soon when they will be available. Everything is open source, the hardware, PCB files, firmware, all the tools. Contribution, suggestion, improvement are always welcome. The build guide for the calibration, everything is on GitHub. Almost all the presentation is there also with all the details. So thank you everyone for listening to my presentation. If there is any question in English or in French, I can answer. Yes.
What does the long pulse signify?
It's mostly used by turbo loader because they don't use a synchronization bit usually, so they rely on that. So when to switch to turbo mode, they just check the pulse length and they decide if it's a 0 or 1, and they usually push that in a shift register and they construct the byte. So when they see the long pulse, they know that it's probably another file, let's say, or component of the tape to load. Question?
One more.
Yeah.
The data is digital, purely digital, but what does the waveform look like?
A little bit like I did, but it's mostly square. Yeah.
Okay.
Yeah, with some degradation in the signal when you observe it. Yeah.
So it's an analog version
Yeah.
of the digital pulse.
Yeah. So when internally, when there is a transition in the TTL signal that you send to the dataset, the electronic is doing a kind of curve like this when driving the current inside the head. So this is what you see on the scope, and no more transition after. Yeah.
So I'm not sure if I missed this, but did you say that within your software you have the ability to adjust the azimuth? Like it has that built into it?
Yeah. I can show it back to you. Yeah, here. So during the capture, if you use a long tape, like I was showing in the demo, if you see something like on the left, that's not good. So you can, while it's capturing, you can adjust the screw on the top of the dataset to try to converge to something like this.
Okay, thanks.
That's it. Yeah.
So, I'm really ignorant of the cassette format. Does it have, when it encodes the data, does it encode check digits, or does it just encode the pure binary numbers with there's no way to tell if the it's common in digital format to sometimes store with a checksum or check digit.
Yeah. Especially not for turbo loader, but for the regular Commodore loader, they have. I didn't went into the details because for this project, it's only at the very low level that we work just for the pulse itself. But when you start checking the type of pulse, the 0, the 1, and the synchronization, they built a whole protocol on top of that, where they have block, header, the data, some error correction on top of it. Like I was saying, they duplicate also each block. So you can find the documentation on the web about this, but they structure it this way. I think it's around 180 bytes per block of data and some padding for the header and error correction.
Thanks.
No problem. And they have different type of block, if it's the beginning of the file with the file name, or if it's purely data. So but for this device, at the end, it's just pulse duration that we want to monitor. So we don't care about this. Thank you.